Hi guys, today we're going to talk about real numbers and the properties of real numbers, which might make you wonder, are there unreal numbers? Well, we'll talk about that a little too. So let's dive right in. So this diagram shows the categories of real numbers, and two main categories, or the division here, is between the rational numbers on the left and the irrational numbers on the right. And within the rational numbers there are a lot of subcategories. So we'll start in the middle, and this is sort of like going back in time to the first numbers that people used. It was primitive people counted. You might count how many fish you caught, tell your friends, hold up that many fingers, and that number meant something. 3 fish, 2 fish. But they may not have talked about fractions. They may not have had the number 0. So these are called the natural numbers. They occur naturally. It's natural for humans to count. So that's just the numbers 1, 2, 3, and so on. Does not include 0. Whole numbers encompass all the natural numbers, but also include 0. Integers encompass all of the whole numbers, but they also include the negatives as well. Okay? -1, -2, -3, and so on. And then rational numbers include the integers, but everything else that can be written as a fraction. Integers themselves can be written as fractions. We have 1 and 2 in this list as examples. 2 can be written as a fraction, 2/1, right? And here are other examples. -1/2, 0.222. That's a decimal representation, but that's just 222 over 1,000, right? It's a fraction. 2/3, 5/6, 6.1. These are all numbers that can be written as fractions. So that's the rational numbers. The irrational numbers, or the other category of real numbers, they cannot be written as fractions. Here are some examples. √2, √3, pi. It seems a little odd, a little mind-blowing to me. It always did, especially when I first learned this, that there are numbers that can't be written as a fraction. Surely you can write it as a fraction. If you used a large enough denominator, there's got to be a way to do it. It might be a denominator up in the billions, but whatever this number is, you could write it as a fraction, right? But actually you can't. You just cannot write these numbers as a fraction. Just a little bit of the history of that's interesting. The ancient Greeks were really bothered by this. They thought of numbers mainly in terms of distances and lengths in geometry. And if you have a triangle, let's see, we'll just draw a triangle here. A right triangle where both sides are the same length. Am I close here? Not real close. But we'll say both sides are the same length. The Pythagorean theorem says this hypotenuse is the square root of 2. And don't worry about that if you don't remember. It's okay. But they knew that hypotenuse had to be the square root of 2, and that's a distance, and they thought all distances should be able to be written as fractions. I mean, come on. Fractions were as deep as their system of numbers went. They had whole numbers, They had fractions. They thought that should cover it. You know, it's natural to think that. If you're like me, you probably are thinking, yeah, fractions ought to cover it. You ought to be able to write that as a fraction. Turns out you can't. And this was pretty disturbing. There's a legend that some of the disciples of Pythagoras murdered the guy who figured out that you can't write square root of 2 as a fraction. I don't know if it's true. They were so upset, they said, we just got to get rid of this guy. But it turns out you cannot write these numbers as fractions, and there are a lot of other numbers too. It can be proven. You can look up videos on YouTube to see the proof of it. It's not a real complex proof. There's a few different ways to prove it, maybe several. But it's kind of interesting to look at an actual proof that the square root of 2 cannot be written as a fraction. Okay, so let's go on. We have a few more notes here about sort of the nature of these different categories of numbers. We use natural numbers to count, as I talked about. Whole numbers are natural numbers, including 0. Integers are the natural numbers, their opposites, and 0. Okay. So here's just some more information to sort of clarify the difference between rational numbers and irrational numbers. Rational numbers are all the numbers you can write as a quotient of integers. A over B, where B is not equal to 0. Okay, the denominator can't be 0. They include terminating decimals. How do we know that a terminating decimal is a rational number? Well, here's an example. 1 over 8 turns out to be a terminating decimal, 0.125. If it's terminating, that could be written as a fraction over a power of 10, right? So this is 125 over 1,000. And that's not in lowest terms there, because 1 over 8 is the fraction in lowest terms. But a terminating decimal can always be written as that number, in this case 125, those digits, over the correct power of 10. In this case, because there are 3 decimal places, right? 1,000 is the power of 10 in the denominator. So they include terminating decimals. They also include repeating decimals. So 1/3 is a fraction, but when written as a decimal, it turns out to be 0.3 with the 3 repeating. And this is just the nature of fractions. When you put them in a decimal representation, sometimes they repeat forever. And that's just the way it works out. And those things that repeat forever, we know those are always going to be rational numbers. There's always a way to write them as a fraction. Another example, if you ever see 0.66, this time I'll go ahead and write some of the 6's. You don't have to. We could just write a single 6. But 6 repeating, that is equal to 2/3. Okay, so anytime it's a repeating decimal, you know it's going to be able to be written as a fraction. That's just the way it works out. Okay, so irrational numbers cannot be written as quotients of integers. And they have decimal representations that neither terminate nor repeat. So pi, for example, do you know some of the digits of pi? I don't know a whole lot. 3.1415926. And then we write dots down here, meaning yeah, it keeps going. There's more and more digits. You keep writing digits, but it's never going to repeat. Square root of 2. I don't know very many digits of it. I believe it's 1.4, and then I believe a 1, and then it keeps going. You can calculate digits all day long for these numbers. There are ways to calculate digits and keep adding digits to them, but it's never going to repeat. Okay. We can graph these numbers, show where they are on a number line. Whether they are rational or irrational, they can be placed on a number line. So just because you can't write it as a fraction doesn't mean you can't put it on a number line. It still has a spot. And that's why we call this the real number line. It includes all the real numbers, rationals and irrationals. So, for example, -5/2 goes right here because that's -2.5, right between -2 and -3. Square root of 2, we can approximate it. It's about 1.4, as we just said. So you could put it right there on the number line. 2.6 with the repeating 6, that's going to be about 2 2/3. So it goes about right there between the 2 and the 3, but closer to the 3. That is the real number line, which that reminds me of the question, are there such thing as unreal numbers? Those would be numbers that are not on the real number line. And there are numbers called imaginary numbers. And that's all I'm going to say about them right now. I'll mention imaginary is not really a great word to describe those numbers. I think we get to them in chapter 4. Okay. So you can graph these numbers. You can also order these numbers. You can always compare any real number to another real number, and it's going to be less than or equal or greater than, okay, another real number. You can compare rationals to irrationals. That's a little tricky with the actual math that has to be done. We don't have to worry about it. We would just use an approximation of the irrational number and get out enough digits to know whether or not it's greater or less than the rational number we might be comparing it to, because you can always calculate the digits for these numbers, even though you can't write them as fractions if they're irrational. So let's do this. Compare square root of 16 and 3.8. So that's going to be, the square root of 16 is 4, right? So we would be comparing 4 and 3.8. Well, 4 is greater than 3.8, right? So that's the answer there. We could write it this way: square root of 16 greater than 3.8. Okay, so what about -2 and -2.1? This is important to realize. Let's -2, -2.1. What's the symbol that goes in there? It's not equal, obviously. Is it greater than or is it less than? Okay. It's actually greater than. So you think of a number line, and the number line has negative numbers and positive numbers. The one that's the farthest to the right is greater. Okay, so -2.1, is to the left, correct? It's to the left of negative 2. So the one to the right is greater, the one to the left is less. So negative 2 is greater than negative 2.1. We can talk about the magnitude of numbers and the absolute value of numbers, and that's where, yeah, negative 2.1 has a larger magnitude. It has a larger absolute value than negative 2. But right now, we're not talking about that. We're just talking about the numbers themselves, and negative 2 is greater because it is to the right. It's farther to the right. Negative 2.1 is less than negative 2 because it's farther to the left. So, okay, next example, we're going to order these from least to greatest. So, you just have to evaluate each close enough to compare it to the others, right? So you have 2/3, you have square root of 9, that's 3. That's the very biggest one on here, right? What's the least? The least would be the one that's the most negative. That's the farthest to the left. So the one that's the most negative out of all these is negative 1.2. So that would be our first one. And then there's another negative. There's only one more negative, so that would be our next one as we move from least to greatest. And then no more negatives. Well, there's 0. That's going to be less than the positive ones. Now we got to look at the positive. The smallest positive one here is the fraction that's less than 1, so that's 2/3. And then we have square root of 9 is 3, so that's bigger than 2.5. So 2.5 is next, and square root of 9 is last. So those are ordered. Let's look at this next example again from least to greatest. The one that's the most negative, the farthest to the left, will be the least, and that is negative 4.6. Next is negative 4. Next, there's only one more negative, that's negative 2. 0's not here, so now we're going to be into the positive numbers, and we want the smallest positive number. Which of these numbers? That's 1 1/3. That's only about 1.3 something, right? Smaller than 1.7. 1 1/3 is next. And then I believe 1.7 is next because the others are larger, and that leaves 5.5 and 5.3 are the last two to place in our list. 5.3 is smaller. That's 5 3/10, where 5.5 would be 5 5/10. If you convert them both to tenths, that's one way to compare them, or just realize that 5.3 is less than 5.5 is another way to look at it, because 5.5 is 5.5. Okay, so there they are in order. Okay, so we have to look at the properties of real numbers now. Now that we've got an idea of what they are, how they can be compared to each other, how rationals and irrationals, both being real numbers, they reside on the same number line. We can compare them to each other. Now let's look at the properties of real numbers. And you've seen these before. The commutative property applies to addition and multiplication. We talk about the commutative property of addition, and the commutative property of multiplication means that the order does not matter. When you add things, order doesn't matter. When you multiply, order doesn't matter. A plus B equals B plus A. A times B equals B times A. Either order that you use, you get the same result. Associative is about grouping. We did not change the order here. It's ABC, ABC. The order is the same, but you can group the A plus with A plus B together and do that first, and then add C, or you can group B plus C together and then add A. Multiplication, same thing. The grouping does not matter. Okay, and there it is. Identity property, there's an identity for addition, there's an identity for multiplication. That just means there is a number, we call it 0, that you can add to any number and you get the same number back. Okay, that's the identity property. For multiplication, the identity element, we would call it is 1. So the property means, yep, there's a number that you can multiply by any number and you get the same number back. A times 1 equals A. Doesn't matter what A is, if it's a real number, multiply by 1, you're going to get A. Inverse property just says there is an inverse for any real number. That when you add a number to its inverse, you get 0. You get that identity element. I wrote my zeros differently, so I'll try to fix that. The same number that you add to things and doesn't change them, you can get that number back by adding. You obtain that number when you add a number to its inverse. There exists an inverse for any real number is really a better way to say that. It does exist for any real number, and when you add that inverse to a number, you get 0. And for multiplication, the identity element is 1. So we're saying there's an inverse for any real number that you can multiply that real number by to get 1. We call that the reciprocal. A times 1 over A is 1. And last, the distributive property says A times the quantity B plus C is the same as taking A times B plus A times C. So there's the properties. I'd like to just pause a few seconds to think about where these came from. Why do we say these are properties? Who says? Says who? These are the properties of real numbers. Basically, human beings decided these are good properties to use. It's a decision made by mathematicians over the years. Somebody came up with this. They kind of agree. Yep, let's do that. But why? Why did they pick these properties? And you've probably realized when you look at these make sense as properties. When we add things together, the order doesn't matter. If I have 2 puppies and someone gives me 3, I'm going to get 5. But if I started with 3 and someone gave me 2 and added them in the other order, I still got 5 puppies. So they represent the way operations on these quantities actually work. Multiplication, the same thing, and it might not be obvious with multiplication. We know it becomes obvious after a while. Yeah, it doesn't matter which order you multiply. 3 times 5 is 15. 5 times 3 is 15. Yeah, it doesn't matter. But it actually, you can do a little exercise and kind of prove to yourself that it's always true with a little grid. It makes sense. This is the way quantities work. Oh, better plug in a battery. so so we have this grid, and you can look at that grid and say, well, that's 3 rows of 5, right? So that's 3 times 5. But you could also say, well, that's 5 columns of 3. There's 5 of them. 5 of 3. There's 5 of those 3s. 5 times 3. 5 of these columns of 3 each. So, well, you know, regardless of whether you think of it as a certain number of rows or a certain number of columns, it's the same grid, it's the same dots, so you don't change the number. So multiplication is commutative. The number of dots is not going to change, it's going to be the same. And in this case it ends up being 15. But anytime you have rows and columns like that, you can think of it either way, meaning you do the multiplication in either order. The number of dots is not going to change. So, you know, these other properties are like that. They arise from the way that quantities work and in real life. Distributive might be a little tricky to think about, but just briefly we could say, well, look, if you have 2 stacks of cartons of eggs, okay, this is a carton of egg, there's another carton of eggs, another carton of eggs, each carton has 12. So this stack has 3 and this other stack has 4. I'm not very good at drawing cartons of eggs. Okay, so how many eggs do we have all together? Well, you could say, well, I'm going to take a shortcut. I got 7. I got 3 plus 4. That's how many cartons I have. There's 12 eggs in each carton. So that's my answer, right? 84. Or you could say, well, I'm going to calculate each stack separately. So I've got in my left stack 12 times 3, because each one has 12 and there's 3. In my other stack I have 12 times 4. Okay, and if you calculate that, yeah, it's also 84. Did I do the math right? I think so. So, and we know either way, no matter what the exact numbers we're using here, the number of eggs isn't going to change, right? So, yeah, it's the same. The distributive property works. You could calculate it either way and you get the same number. So A times B plus C will always equal A times B plus A times C. Okay, and I won't talk about the others, but they also make sense. They also work. That's why we use these properties. You might wonder, well, people could make up any properties they want. What if they said addition is not commutative? What if they said A plus B may not always equal B plus A? You could make some math that might be interesting, but you wouldn't want to use that math when you go to the grocery store, because you're adding up your all your purchases and you suddenly realize it makes a difference which order they're in. Oh my gosh, I'm paying more because I took these out of my shopping cart in the wrong order. So yeah, it would be a really strange mathematics. Wouldn't correspond to everyday life. But you know, sometimes people do math, they don't care whether it corresponds to real life or not. They just think the math is interesting. So yeah, you can have a number system. It would not be our real number system. It would be some other number system where some of these properties aren't true. And there actually are number systems like that. There maybe it's not correct to say number systems, let's say mathematical systems, where some of these properties don't hold just because the people designing that mathematics decided they don't want these properties to hold. So we don't have to worry about that. We're just talking about properties of real numbers. Let's go on. So look at these examples, and actually I'll leave the properties on there while we look at them. Which property is represented by this first one? Negative 2/3 times negative 3/2 equals 1. Which property is that? That is the inverse property of multiplication. Let's see, let's go with blue. We'll release the rest of the letters. Okay, what about this next one? 3 times 4 in parentheses times 5 equals 4 times 3 in parentheses times 5. Which property is that? They're saying those two things are equal. Be careful with this one. You see the parentheses, you might think this is the associative property, but look at the grouping. The grouping didn't change, right? 3 is grouped with 4. 3 and 4 are also grouped together here. The associative property says you can change the grouping and you won't change the result, but that's not what we changed here. So what did we change? We changed the order, actually. 3 times 4 became 4 times 3. The property that says you can change the order without changing the result is the commutative property. And in this case, we say the commutative property of multiplication. Okay. So the last thing we're going to look at is just some examples. Tell whether each of these is rational or irrational. So look at this first one. That rational or irrational? Okay, there's a pattern here. You say 3, 0, 3, and then 2 zeros and a 3, and then 3 zeros and a 3. Is that a repeating decimal? If it's a repeating decimal, it's rational. But it's not really a repeating decimal, okay? Just because a pattern shows up like that, to be a repeating decimal means there is a sequence of digits that actually repeats. This does not. It's different every time. There's more zeros. It's not repeating. That's irrational. We'll just write an I. Okay, what about this one? Okay, this says the 2, 1 repeats. It's 2, 1, then 2, 1, 2, 1, 2, 1, 2, 1. It repeats. So because it repeats, that's rational. The square root of 8. Now what we would do with that is simplify it as much as we can to see if it comes out to a rational or irrational number. So if you remember how to do this, you can write that as 4 times 2 and inside the radical, and then you can take the square root of 4, which is 2. So we actually calculate the square root of 4 being 2 and pull it out, so to speak, and then that leaves the square root of 2 still in there. So it's 2 times the square root of 2, but the square root of 2 is irrational. Can't be written as a fraction. So multiplying it by 2 is not going to suddenly make it able to be written as a fraction. It's not. That's irrational. Square root of 9, well, we know what that is. That's 3. That can be written as a fraction, so that's rational. Write that a little better. How about the square root of 2/5? Okay, that's going to end up with a square root of 2 in it no matter what we do, right? We could rationalize the denominator. We could write square root of 2 over square root of 5, then multiply top and bottom by the square root of 5. The top becomes square root of 10, bottom becomes 5. But regardless, and actually, let's just leave it. To really show that it's irrational, we just leave it like this. Square root of 2 times the square root of 5 over, on the bottom, square root of 5 times square root of 5 is 5. So that's what it comes out to. I've got a little bit of a mess here. I'm going to circle the answers. So you have irrational numbers there. You have an irrational times an irrational. There's no way that's going to turn it into a rational, okay? You cannot write these as fractions. So multiplying them by each other will not give you a result that suddenly you can write as a fraction. Not going to happen. So that's irrational. And then last, you have the square root of 16 over square root of 9. This one might be a little more manageable. We can take those square roots, right? So the square root of a quotient is the quotient of the square roots. So we write it down like that. Square root of 16 is 4. Square root of 9 is 3. Looks like a fraction to me. We can write that as a fraction, so it's rational. Okay, so that's all we're going to look at. This last exercise actually reminded me of something else I'll briefly mention. Where does this number rational come from? Does it mean these are like reasonable numbers, or something like that? It probably really just comes from the word ratio. A ratio is a fraction, right? So these are rational. They can be written as fractions. Irrational cannot. Okay, so